Hello everyone, welcome to another module in this course, Strategy and Introduction to Game Theory. So, we have looked at a variety of games so far in the different modules up to this point. I hope you are learning and enjoying the theory of games. So, let us start looking at a slightly more different or slightly different variety of games, games with a slightly different flavor than what we have been looking at so far. So, we are going to start looking at what are known as games with mixed strategies or randomized strategies. So, we are going to start looking now at mixed strategies or also what are known as randomized strategies, right. Now, to understand what are mixed strategies, let us take the example of a simple game. This game is also known as matching pennies. This is a game which is titled as matching pennies, and the idea is as follows, that is there are two players, let us say there are two siblings P1 and P2 who have a penny or a coin each, P1 comma P2, these are the two players, they have a coin each. They can show one face of a coin, that is they are free to choose any face of a coin. They can show one face of a coin, they can either choose a head obviously, which we are going to denote by H, or they can come up with the tail face, that is either the head face or the tail face, that is each player P1 and P2 can show either a head or a tail. Now, the catch is that if both show the same face, that is if both show same face, then P1 wins, that is player 1 wins and P2 pays, let us say 1 rupee to P1. So, if both show the same face, then P1 wins and P2 has to pay 1 rupee, let us say a token amount to P1. On the other hand, if both show a different face, then P2 wins and P1 has to pay 1 rupee to P2. And P1 has to pay 1 rupee to P2, right. So, let me just repeat the key idea, P1 and P2 have a coin each, they are free to show either face, that is either a head or a tail, and if the face they show is the same, then P1 wins and P2 has to pay 1 rupee to P1. On the other hand, if both of them come up with a different face, that is P1 shows heads and P2 shows tails, or P1 shows tails and P2 shows heads, then P2 wins and P1 has to pay 1 rupee to P2. All right. So, that is the game, and again let us, similar to what we have done previously, let us formulate this in terms of the game table, right, which is a very convenient way to represent the game, which all of you should be very familiar with. So on P1 and P2, they have two options to either show heads or tails, heads or tails. If both show heads, then P1 wins, in which case he gets 1 rupee and P2 gets minus 1. If both show tails, then again P1 wins, in which case he gets 1 and P2 gets minus 1. On the other hand, if P1 shows heads and P2 shows tails, P2 wins, P1 has to pay 1 rupee to P2. So, P1 gets minus 1, P2 gets 1. If P1 shows tails and P2 shows heads, again P2 wins, in which case P1 gets minus 1 and P2 gets 1, right. So, this is the game, right. This is the game. This has row player P1, column player P2, each has each has to choose one action, that is heads or tails represented by H or T. Now, of course, let us try to find the Nash equilibrium again by the best response. If P2 chooses head, best response of P1 is to of course choose head. If P2 chooses tail, best response of P1 is to choose tails, right, because P2 wins when he matches P1. On the other hand, if P1 chooses heads, best response of P2 is to choose tails, and if P1 chooses tails, best response of P2 is to choose heads, because heads gives him 1, tails gives him -1. And therefore, now you can see in this game there is no intersection of best responses. So, we are now seeing a game table in which there is no intersection of best responses. So, we cannot find the Nash equilibrium of this game using the techniques that we have learnt so far, right. And this is a specific example of a game where each is considering a single strategy. Such a strategy is also known as a pure strategy. So far, we have considered pure strategies where each player is choosing one action. That is, in the prisoner's dilemma, each prisoner is choosing either confess or deny, right. Similarly, in the case of the coordination game, each one is choosing either the deer or the rabbit. What we are going to now start considering are a different set of games in which the players do not need to choose one strategy at every instant, but they can randomly choose between two different strategies with a certain probability for each strategies. That is, we are going to consider games in which players can randomly choose a particular action with a certain probability. That is, that we are considering a game in which, let us take an example of this matching pennies game itself, that is, a player can randomly choose between heads and tails. With a certain probability he can choose heads, with a certain probability he can choose tails, and such a game or such a strategy is known as a mixed strategy or a randomized strategy. This is known as a mixed strategy. Mixed strategy because you are mixing between two different actions, that is, you are mixing between heads and tails, or a randomized strategy because you are randomly choosing one action versus the other. This is similar to, so as to say, randomly choosing one action versus the other. So, this is also known as a randomized This is known as a mixed strategy. This is also known as a randomized strategy where you are randomly choosing with a certain probability, you are randomly choosing, or with certain probabilities you are randomly choosing one action versus the other, right. So, let us now try to analyze this game in terms of randomized strategies. Let us go back to this game. Let us now try to analyze this game in terms of randomized strategy. Let us say player 1 is choosing heads with probability P, and therefore, naturally he is choosing tails with probability 1 minus P. To people who are not familiar with the basics of probability, let me just give a brief recap of the probabilities. The probability is a positive quantity which is less than 1, therefore, the probability P has to lie between 0 and 1. Let us say for example, P equals 1/4, which means player 1 is choosing heads with a probability 1/4, which means player 1 is choosing H with probability 1/4. That means randomly with frequency, that is 1/4 of the times, right, randomly 1/4 of the total number of times the game is played, he is choosing heads, right, approximately on an average 1/4 of the time he is randomly, that is frequency 1/4, that is 1/4 of the total times the game is played, he is choosing heads. So randomly, or you can say with frequency 25%, so randomly 25% of the time he is choosing heads, which means 75% of the time he should be choosing tails, which means the probability of tails is 0.75, or the frequency is of tails is 0.75. So which means the probability (1 minus 1/4) is equal to 3/4. That is to say, on an average 75% of the time he is choosing tails. Therefore, P equals 1/4 means about 1/4 of the total time instance, that is for 25% of the time he is choosing heads and 75% of the time randomly he is choosing tails. Similarly, if P equals let us say 0.6, it means 60% of the time randomly he is choosing heads and 40% of the time, that is P equals 0.6, 40%, 1 minus P is 0.4, which means 40% of the time randomly he is choosing tails. So as P varies between 0 and 1, the relative frequencies of these heads versus the choice of these heads versus tails is also varying appropriately, right. So what we are saying is we are going to start considering a different kind of games in which the players do not need to choose a fixed action, but randomly choose between a set of actions, and we have defined a probability, that is in this matching pennies game. Let us say that the P denotes the probability with which player 1 is choosing heads, then naturally 1 minus P is the probability with which player 1 is choosing tails, right, and this quantity P is a probability, which means it is a positive quantity greater than 0 and less than 1. So 0 lies between, therefore P lies between 0 and 1, right. And therefore what we have already said is, let me draw this table again, so just to illustrate this. Clearly, we are considering a matching pennies game with 2 players P1, P2, each has an option to choose head or tail, and the payoffs are 1, 1, 1, 1, minus 1, 1, minus 1, minus 1, 1, minus 1, 1. Now let us say player 1, and now we also said that player 1 is choosing heads with probability P, tails with probability P. Now let us try to compute the payoffs of player 2. If player 2 chooses heads, that is if player 2 is choosing heads, then with probability 1 P, he will meet player 1, he will find player 1 playing heads, in which case his payoff is minus 1. With probability 1 minus P, that is on average frequency 1 minus P, he will find player 1 playing tails, in which case his payoff is 1. So fraction P of the time he will get a payoff of minus 1, fraction 1 minus p of the time he is going to get a payoff of 1, and therefore, the average payoff of player 2 is, that is, if player 2 chooses heads, his average payoff is fraction p of the time he gets minus 1 plus fraction 1 minus p of the time he gets 1. So, therefore, his average payoff is p times minus 1 plus 1 minus p times 1, which is basically equal to 1 minus 2p, right. So, let me repeat this argument again, because this is at least initially for those who are not very familiar with probability, this can be a slightly tricky argument and also a slightly confusing one. So, let me repeat it so that you understand it thoroughly. We are assuming that player 1 chooses heads with probability p and tails with probability 1 minus p, and if player 2 is always choosing heads, then we have with probability p he meets player 1 or he encounters player 1 playing heads. So, with probability p his payoff is minus 1. With probability 1 minus p he encounters player 1 playing tails, in which his payoff is 1. So, fraction p of the time his payoff is minus 1, fraction 1 minus p of the time his payoff is 1. So, his average payoff is p into minus 1 plus 1 minus p into 1, which is equal to 1 minus 2p. Similarly, now on the other hand, if player 2 is always choosing tails, then fraction p of the time his payoff is 1. Fraction p of the time when p1 is choosing heads, his payoff is 1. Fraction 1 minus p of the time his payoff is minus 1. Therefore, the average payoff this time is p into 1 plus 1 minus p into minus 1, which is equal to 2p minus 1. So, what we are saying is, if player 2 is always choosing tails, then fraction p of the time his payoff is 1, fraction 1 minus p of the time his payoff is minus 1. Therefore, his net payoff is p times 1 plus 1 minus p times minus 1, which is equal to 2p minus 1. So, these are the two payoffs that player 2 receives if he chooses either heads. So, if he chooses heads, his payoff is 1 minus 2p. If he always chooses tails, his payoff is 2p minus 1. Now, this is the situation when player 1 is using probabilities p and 1 minus p. Now, when is, if we think about it, when is player 2 going to randomly choose between heads and tails, because we are assuming that both the players are using randomized or mixed strategies. When is player 2 randomly going to choose between heads and tails? For instance, his payoff from heads is 1 minus 2p, his payoff from tails is 2p minus 1. If the payoff from heads, that is 1 minus 2p, is greater than the payoff from tails, then player 2 is always going to choose heads. Similarly, if the payoff from tails to player 2 is always greater than the payoff from heads, that is 2p minus 1 is greater than 1 minus 2p, then he is always going to choose tails. And therefore, he is going to randomly choose between heads and tails only when the payoff from both of these are equal. And this is an important principle to understand. One would randomly mix between two actions, A1 and A2, only if both the actions yield an identical payoff. Another way of saying this is that the player is indifferent to both these actions. Therefore, P2 would mix or randomly choose between H comma T only if both payoffs are equal. Therefore, he would randomly choose between head and tail only if both payoffs are equal. If the payoff from head is greater than tail, then he would always choose head. If the payoff from tail is greater than head, then he would always choose tail, and he would randomly choose between of one versus the other only when the payoffs of both of them are equal or he is indifferent to both of them. And therefore, for a mixed strategy Nash equilibrium, for a mixed strategy equilibrium, that is for player 2 to choose randomly between heads and tails, it must be the case that u2 of heads equals u1 of or u2 of tails, which means I have to have 1 minus 2p equals 2p minus 1, which means I have 1 minus 2p equals 2p minus 1, and solving this I get 1 minus 2p equals 2p minus 1, which means 4p equals 2, which means p equals half. And therefore, what this says, if p is equal to half, that is when p is equal to half, when player 1 is choosing heads with probability half and tails with probability half, that is he is randomly mixing or he is randomly choosing heads 50% of the time and tails 50% of the time, it makes sense, or P2 is going to employ a randomized strategy, because in only that scenario his payoff from heads, which is equal to 1 minus 2p, is equal to his payoff from tails, which is 2p minus 1, and therefore it makes sense for him to choose BT to employ a randomized strategy. So in turn we can also say that the strategy employed by P1 for a mixed strategy Nash equilibrium should be such that, or the probability chosen by P1 should be such that P2 or player 2 becomes indifferent to choosing between heads and tails, and only then he is going to randomly choose between heads and tails. And therefore, we get equating the payoff to player 2 from heads and tails, we determine that P is equal to half. And this is an interesting aspect. Determine the mixture of player 1, that is to determine the probability P of player 1, we have to look at the payoffs of player 2, and we have to find that point at which player 2 is indifferent between these two actions, and that is what we said. And he is indifferent between these two actions when the payoffs are equal, that is 1 minus 2p equals 2p minus 1. Now let us similarly find the mixture for player 2. Let us assume player 2 is choosing heads with probability q and tails with probability 1 minus q, where again q is a probability, therefore we have to have 0 less than equal to q less than equal to half, right. So player 2 chooses h with probability q and chooses t with probability 1 minus q. Again, to determine q, remember we have to look at the payoffs of player 1, right. To determine the parameter, the mixture of player 2, we have to look at the payoffs of player 1. Now if player 1 chooses h, his payoff to choosing h is with probability q, he encounters player 2 playing h, in which case he gets 1. With probability 1 minus q, he encounters player 2 playing tails, in which case he gets minus 1. Therefore, his payoff, that is fraction q, he gets a payoff of 1, fraction 1 minus q, he gets a payoff of minus 1. Therefore, his average payoff is q times 1 plus 1 minus q times minus 1. So his average payoff to always choosing heads, the payoff of player 1 to always choosing heads is q times 1 plus 1 minus q times minus 1 which is equal to 2q minus which is equal to 2q minus 1. All right, let me repeat that argument again. If player 2 using a mixture is using a mixture q 1 minus q, that is with probability q he is choosing heads, probability 1 minus q he is choosing tails, then the average payoff of player 1 for always choosing heads is q times 1 plus 1 minus q times minus 1 which is basically 2q minus 1. Similarly, if player 1 chooses tails with frequency q or with probability q, he is going to encounter player 2 choosing heads, in which case his payoff is minus 1, and with probability 1 minus q he is going to encounter player 2 playing tails, in which case his payoff is 1. Therefore, his average payoff is q times minus 1 plus 1 minus q times 1, right. So, average payoff of u1 if he is always choosing tails is q times minus 1, q times minus 1 plus 1 minus q times 1. With probability q, he finds player 2 playing heads, in which case he loses 1 rupee. So, it is probability. So, his average payoff is q into minus 1 plus with probability 1 minus q he finds player 2 also playing tails, in which case he wins 1 rupee. So, that contributes 1 minus q times 1. So, his net average payoff is q times minus 1 plus 1 minus q times 1, which is equal to 1 minus 2q. So, as a function of the probability q or the mixture q employed by player 2, the payoff to player 1 for always choosing heads is 2q minus 1. The payoff to player 1 for always choosing tails is 1 minus 2q. Now, of course, again repeating the same argument, if 2q minus 1 is greater than 1 minus 2q, then player 1 will always choose heads. On the other hand, if 1 minus 2q is always greater than 2q minus 1, then player 1 will always choose tails. He will randomly choose between heads and tails only when he is indifferent to one versus the other, that is when he will randomly player 1 will mix or employ a mixed strategy only when his payoff u1 from heads is equal to u1 from tails implies that 2q minus 1 equals 1 minus 2q, and solving this we have we have 4q equals 2 implies q equals half. So, again what we are finding is that for player 1 to be indifferent between heads and tails, to use a randomized strategy or a mixed strategy, we have to have q equals half. That is, the mixture employed by player 2 should be q equals half, which means 1 minus q equals half. Therefore, he is mixing heads and tails with probability half and half. So, we have q equals half, 1 minus q equals therefore also half. Therefore, P2 is mixing h comma t with probability half comma half. Similarly, we have p equals half implies 1 minus p equals half. Therefore, P1 is mixing h comma t with probabilities half comma half. Therefore, the mixed strategy Nash equilibrium for this game can now be formulated as the mixed strategy Nash equilibrium or the randomized strategy, the mixed strategy Nash equilibrium for this game is now given as, well, we have to give one mixture for each player, that is half comma half for player 1, half comma half for player 2. So, this is the mixed strategy or player 2 for player 1, and this is the mixed strategy of player 2. What do we mean by a mixed strategy? A mixed strategy basically denotes the probabilities with which each player is mixing the various actions. So, half comma half says that player 1 is randomly choosing between heads and tails with probability half each, and half comma half for player 2 says that player 2 is also randomly choosing between heads and tails with probability half each, and these two mixed strategies are part of this mixed strategy Nash equilibrium. So, at Nash equilibrium player 1 is randomly choosing between heads and tails with probability half, and he is choosing, and player 2 is randomly choosing between heads and tails with probability half, and this is the mixed strategy Nash equilibrium for this game. So, today we have learnt a new concept which is a mixed strategy Nash equilibrium. In comparison, in contrast to the previous games where we had looked at pure strategy Nash equilibrium where each player is choosing a pure action, in a mixed strategy Nash equilibrium each player is randomly choosing one action against the other, and we had considered a matching pennies game. Remember, we said that this matching pennies game does not have any Nash equilibrium in pure strategies. On the other hand, it has a Nash equilibrium in mixed strategies where each player is mixing heads and tails with probability half. And also it is worth mentioning at this point that it turns out that the mixture is exactly half, that is the probabilities of both the actions are equal and the mixtures are the same for both the players, but these need not be true for a general games. That is, the probabilities for all the actions for the different actions can be different, and also the mixtures for the different players can be different, and we are going to look at some examples of games that have this property, that where these probabilities are different in future examples. So, this is again a different kind of a game. I hope you have understood it. Please go through the lecture again and try to understand it thoroughly if there are some aspects which are not clear. All right. Thank you very much, and we will conclude this module here. Thank you.